Our goal is to provide mobile robots with an understanding of large-scale environments that will enable them to act reliably in collaboration with humans. Spatial knowledge exists at different scales, from objects, places to whole buildings, and at different levels of abstraction, from sensory data, place appearance to high-level semantic descriptions. Yet, robot sensory observations are local, partial, and noisy. At the same time, a robot can exploit general relationships that govern the human world to resolve ambiguities and infer latent concepts. Unfortunately, such relationships are difficult to incorporate into the inference process. This often leads to approaches that are either a collection of independent components or deep networks that span only portions of environments. To overcome these shortcomings, we present an end-to-end unified deep network for modeling semantic maps, which represents complex relationships across levels of abstraction as well as local and global space. The network adapts to the topology of the environment and represents uncertainty in spatial knowledge. It is a sum-product network, which makes it a probability distribution that can be learned directly from high-dimensional data, yet affords tractable and exact inference. We learn the network in semantically annotated training environments. As the robot explores each environment, it integrates laser range data into local maps representing the geometry of each place. A topological graph relating the places is expanded as the robot moves around. Our unified network is a deep template model assembled from template networks learned to represent specific recurring structures in the environments. Each such structure corresponds to a subgraph of the topological graph. During learning, for each subgraph, we learn a template network using all training data extracted from matching parts of the training environments. When the robot explores a new environment, the full model is built for the current state of the topological graph. To this end, we first decompose the graph into subgraphs identified during training. For each subgraph, we instantiate the corresponding template and we combine those into a network representing the whole environment. The complete network is a mixture of several such decompositions. It forms a distribution over all semantic attributes and all pixels for all places in the environment. As a result, the problem of semantic mapping corresponds to inference over semantic attributes given place geometry and topology. Additionally, the network can estimate the likelihood of all the spatial information acquired by the robot within a building. This can be used to detect novel environments with global structure incongruent with the training data. We learned the network on 3 floors of an office building and tasked it with understanding of another floor. Here we show topological graphs of the test floors with colors indicating semantic categories for each place. The ground truth is shown on the left, while the image on the right shows the most likely semantic class as inferred by the network. The network successfully inferred the semantics of 93% of places in our test environments. For results on novelty detection, we refer the viewer to our paper.